Okay, there was a comment that my audio might be distorted, but Chad, if you can hear me, please, you can continue with the introduction.
Okay. Can everybody hear me now?
Yeah, everything sounds good.
Okay, great. Again, my name is Chad Kusko. I'm the operations manager here at the LEHIGH experimental facility. I wanted to thank you for taking the time to attend today's LEHIGH seminar series presentation. The title of today's presentation is The Seismic Behavior of Wide-Flange Steel Columns, Recent Experimental and Numerical Research Findings. Today's presenter is Dr. Ahmed El-Kadi. He's a lecturer in structural engineering within the National Infrastructure Laboratory at the University of Southampton in the UK since August 2019. He holds Masters of Science and PhD degrees from McGill University in Canada. And through integrated experimental, numerical, and analytical research, his research focuses on quantifying structural robustness metrics such as collapse, demolition risk, and direct economic losses of steel and composite steel concrete structures under multi-hazards. His past research has contributed to North American seismic design provisions and the nonlinear modeling guidelines related to steel moment-resisting frame systems. After Dr. El-Kadi's presentation, we will have some time for questions, so please feel free to submit your questions during it, or we can wait till after and take questions at that time. Turn it over to you, Dr. El-Kadi. Thank you again for your time today.
Thank you, Chad, for the introduction, and hello to everyone who are joining us. Let me start by sharing the screen. Can you see it now?
Yes.
Yeah, we can see your screen.
Okay, all right. So hello to everyone again, and as the title indicates, I will be presenting today a summary of recent experimental and numerical research related to the seismic performance and stability of wide-flange steel columns. Now, I would like to mention that this research was conducted over a span of about 6 years. So clearly a number of people, institutions, and funding agencies contributed to the work. Those I would like to acknowledge here in this slide before I proceed. So I'll start with a quick background to the topic by talking about buildings designed with steel special moment resisting frames in highly seismic regions, where the current practice involves concentrating the seismic resistance into few planar frames with a small number of bays at the perimeter of the building, as we see here in this illustration. Now, to comply with the design drift limits, the beam size is typically controlled by the stiffness. And in the same time, the column strength must exceed that of the framing beams to satisfy the strong column weak beam criterion. Eventually, we end up selecting deep members for the columns. Now, these column cross sections typically have depth larger than 16 inches. So we typically see W24s and W30. And these are all have large in-plane moment of inertia as we want. In the same time, to economize on the steel weight, we select cross sections with local slenderness close to the compactness limit for highly ductile members, as per the seismic provisions. And to give you an estimate, roughly the web slenderness would be 40, and the flange slenderness would be close to 7. Now, because of these characteristics, potential problems may occur, including local instabilities and essentially the early occurrence of local buckling and how fast it progresses. In the same time, global instabilities can take place, such as twisting and lateral torsion buckling. And these are all deteriorating mechanisms that we don't like to see, since they trigger a global collapse. Now, this issue can actually be inferred from past cyclic tests on steel beams. For instance, looking at this plot on the right here, we observe that beams close to the slenderness limit may develop limited plastic rotation capacity of about 3 or 2% radian prior to local buckling. and that's without axial loads. So you can expect this issue to be more critical in columns. As you probably know, moment resisting frames are expected to dissipate the seismic energy through the plastification of beam ends. A plastic hinge can also occur at the first story column base, but other than that, the columns should remain elastic to maintain the structure integrity and the gravity load carrying capacity. Now, of course, this is not always the case. Numerical and shake table tests showed that you can get plastic hinges in columns at higher stories. And this is due to several reasons that are not considered in design. For instance, ignoring the beam strength amplification because of the composite action of the concrete slab can lead to a reverse situation where the column becomes the weaker element in the joint, leading to story mechanisms as the one that you see in this slide. In the same time, subassembly tests also showed that once the beam buckles, the lower flange tends to kick out of plane, exerting twisting and out of plane bending demands on the column. Again, this can be a critical issue given the column's geometric properties that I just mentioned. Now, excluding the past 5 years or so, there has been limited number of tests on compact wide-flange steel columns, essentially the ones you see summarized here. And those involved either shallow or stocky cross-section sizes that are not representative of those used in current practice. And although most of these tested columns had a robust cyclic performance, some of which still had limited ductility, even at moderate axial load levels. In the past 5 years, there has been several testing programs on steel columns. In today's presentation, I will present the findings from 2 of those testing programs. Now, the research scope is essentially to investigate the cyclic behavior of deep columns through experimental research or experimental testing and complementing this with numerical simulations. The specific objectives are to reassess the seismic local compactness limit, as well as the global slenderness limit for highly ductile members. Also to develop updated force deformation relations for the nonlinear modeling of steel beam columns, and this was part of the ATC 114 project. We also would like to quantify key column response indicators, such as the plastic hinge length and the amount of axial shortening resulting from local buckling. So the first phase, or the first phase of the research and the first part of this presentation comprises of 2 testing programs, one conducted at full scale and the other at larger scale for a total of 24 column specimens. Looking at the cross-section space for white flanges, for the testing, we started by selecting representative column sizes. So for the full-scale testing program and based on code-compliant archetype mid-rise steel office buildings, we chose W24 by 146 and W24 by 84 to be tested. For the larger scale testing, we selected 3 sizes from W14 and W16 as shown here. And these are equivalent to the moment frame columns in mid-rise steel buildings, but at a 2/3 scale. Probably you already noticed that from this plot that the main geometric parameter that we are varying here is the web slenderness ratio. And essentially, we found this to be the parameter with the most impact on the cyclic behavior of the column based on an exploratory numerical assessment. Now, it's already well established in literature the dependency of the structure component behavior on the loading history applied to it. So in that respect, we aimed to employ a range of loading scenarios in these testing programs. For lateral loading, we applied both monotonic and cyclic lateral drifts. For cyclic loading, we used the standard symmetric ramped AIC protocol, the one typically used in literature to test different structural members and also used for the pre-qualification of beam-to-column connections. Understandably, this protocol may be appropriate for drifts up to 2%, but it's not representative of drift demands at large seismic intensities. And for that reason, we also used what we call a collapse consistent protocol that represents pretty much the asymmetric drift demands under strong earthquakes that induce collapse. And lastly, based on three-dimensional nonlinear analysis, we developed equivalent bidirectional protocols shown here that statistically represent the bidirectional drift orbits using these elliptical orbits that you see over here. Likewise, based on system-level analysis, we evaluated the column axial load demand. Essentially, if you are looking at interior columns, you will see that the axial load demand is the one induced by the gravity load, and it remains more or less constant during shaking. Typically, about 20% of the column axial yield strength, which is what we call here PY, this is what you find in interior columns. If you are looking at exterior or end columns, you will see that they experience varying axial loads due to the overturning of the building. And the range of this variation depends on the seismic intensity and the building height, among other factors. So based on this evaluation, we chose a number of constant and varying axial load ratios to employ in our test. If you look here, the varying axial load essentially includes a constant component representing the gravity offset, or what we call PG. And then you have a transient component representing this variation due to the overturning moments. And for the constant axial load, we went from 20% PY up till larger axial load levels of 70% PY, which may be actually representative of columns in older constructions. A brief word here about the instrumentation. And in addition to the standard force displacement acquisition that we typically do in such tests, it's worth noting that we installed a large array of strain gauges, about 54 gauges per specimen. And this is to capture the neutral axis shifting in the cross section and to track the extent of plastic strains at the column end, and also to allocate or track the location of the flexure inflection point throughout the test. We also use the wireless tracking system to measure the out-of-plane deformations and the twisting of the column along the height. So the first testing program was conducted at the Jamieson Structures Laboratory in McGill University, Canada. In this program, we tested 12 large-scale cantilever columns, the W14 and W16 that I mentioned earlier. These are, each one is 6.5 feet or about 2.2 meter long, representing pretty much the length up till the inflection point. In this one, we subjected the columns to monotonic and cyclic drifts. In monotonic loading, we reached large drifts levels of 15%. So we can characterize the behavior up till these large levels of drifts. In the same time, the drifts were coupled with high constant and varying axial loads, reaching 75% of PY, which provided a unique data set, as I'll show later on. In this slide, I will show, you will see a video of the damage progression in one of those tests from different angles. And essentially in this specific one, the column is subjected to cyclic symmetric drifts and varying axial load. So essentially when we are pushing to the right, the axial force increases. And when you are pushing to the left, the axial force decreases, and it goes, in some excursions, it goes to tension. So actually, based on this, you will notice that when you go to the tension excursion, you will see that the local buckling developed in the left flange tends to straighten once you apply tension to the column. The second testing program was conducted also in Canada at the Structural Laboratory of École Polytechnique de Montréal. And this one involved 10 full-scale 13 feet or about 4 meter long specimens. We were actually fortunate to use this unique 6 degrees of freedom control system that you see over here that was brand new at the time of testing. Actually, for this, I would like to acknowledge the assistance and support of Professor Robert Tremblay of EPM and the lab staff over there. Basically, this system consists of a total of 8 actuators connected to this top platen. And this enabled us to apply bidirectional drifts at the column top and to simulate also realistic boundary conditions. As you can see here in some of the tests, we applied predefined rotation at the column top to simulate the flexibility of the top beam to column joint. This is another video of one of those columns. This particular one had W24 by 84 cross section and was subjected to constant axial load in compression and bidirectional drift with a flexible top end. So here you will actually see that we are controlling 4 degrees of freedom simultaneously. What you probably will notice in this video that the plastic deformation will form first at the column base, the fixed end pretty much. And once local buckling start occurring at the base, and which is right now, and then damage start to progress, the inflection point will start to push downward and the moment demand will increase at the top, and eventually the top end plastifies under further loading. You can also see here what's happening in the out of plane in terms of deformations and twisting. Now, due to the time constraint, I will show you selected observations and findings from these tests, but please feel free to refer to the original publication shown here for the full details. The same applies for the rest of the things I'm showing in today's presentation. So, as you probably observed in the videos, the primary failure mode is local buckling, the progression of which resulted in appreciable amount of column axial shortening, reaching around 50 millimeter or about 2 inches at 3% drift. What's more interesting is that at drifts larger than 2%, local buckling at the base plastic hinge was coupled with out-of-plane instabilities in the form of out-of-plane deformations and twisting of the member. Now, this full-scale test specifically provided the unique data that helped quantify the effect of end boundary conditions, because prior, most of the tests involved either fixed boundary conditions or this cantilever boundary condition as a simplification. So if you look here at, for 2 identical column specimens, but with different boundary conditions, we observed that When it comes to the moment rotation behavior, when it comes to the strength, the differences were minor. However, the differences related to the loss of stiffness was observable. So what happens is that if you look over here for the fixed, the specimen with the fixed top, the column loses the flexure strength and the torsional restraint at both ends simultaneously, leading to almost double the stiffness deterioration level if we look in this plot compared to the column with a flexible top. But with larger drifts, if we start looking at drifts larger than 3%, the weak axis bending demands that are triggered with these large out-of-plane deformations in the flexible case lead to an accelerated loss in stiffness. Again, as you see here, at one point at large drift, now the specimen with the flexible top start losing stiffness at accelerated rate. We can also, from these tests, we can evaluate the effect of the local and global slenderness. And as you may have guessed, you are expecting higher degradation in strength following local buckling for the specimens with larger H over T web or larger web slenderness. But also, more importantly, you will see that we observe that column specimens that have a member slenderness L over Ry higher, they tend to lose stiffness at, again, at a larger rate, and this happens typically at drifts larger than 2%. To further demonstrate the effect of the loading history, you can see here the different responses of an identical column under the symmetric and the collapse consistent protocols. And you probably can see the difference here. Basically, due to the large number of inelastic cycles of the typical symmetric cyclic protocol, damage progresses faster in this case. And to quantify things, you will see that columns under the symmetric loading protocol develop less than half the plastic rotation capacity and shorten at least 5 times more compared to those subjected to the collapse protocol, which tells you that actually symmetric protocols may be as conservative for characterizing column behavior at large drifts associated with the structure collapse at large seismic intensities. We also observed larger rates of cyclic deterioration, specifically at drifts larger than 3%, when we are looking at columns subjected to unidirectional and bidirectional loading. So by looking at this comparison, you will see that essentially under bidirectional loading or biaxial bending, there is a higher rate of deterioration in the strength, especially when you go to large drifts. In the same time, because you are pushing at the top out of plane, you are getting additional weak axis bending, and you are getting larger out of plane deformations, and eventually you are getting higher deterioration in stiffness. It's worth showing also here that this unique setup actually enabled us to evaluate and quantify the out-of-plane force at the column top, where you typically would have bracing. So essentially what we observe that members that have larger member slenderness or global slenderness, L over Ry, will develop lower out-of-plane forces. And the thing here is that the stockier columns tend to buckle later and develop larger amounts of cyclic hardening. And eventually this tends to exert large out-of-plane forces at the top compared to the more slender columns. So again, these are all unique data that has not been measured in prior testing programs. And this also can be used to evaluate the bracing design provisions in the steel specifications, for instance. The second phase of the research involved the parametric continuum finite element simulations to generalize the test findings and to fill the gaps within the experimental data pool. First, we had to develop a robust finite element modeling approach that is defined in an objective manner and that's not biased by test-specific calibrations or model tuning, etc. So this was done systematically. First, we investigated several column members by measuring the local and global geometric imperfections that are product of the rolling process. These mean imperfection values are then deduced and considered in the finite element model. Now, it's crucial that the proper amount of geometric imperfection be added to the finite element model to capture the right response. As I show here in these comparisons, you see that if you totally ignore geometric imperfections in your model, you can be orders of magnitude off when it comes to your prediction. But also when you include geometric imperfection, you have to include the right amount, not too much, not too little, in order to trigger the local and global instabilities at the right time. In the same way, using the sectioning method, we measured the residual stress profiles resulting from the manufacturing process in different cross-section sizes. And from this, we were able to find the most appropriate residual stress distribution that we should consider in our model. Probably the most important part in the model definition is the material model part. And here we used the nonlinear model with the isotropic and kinematic hardening that you typically use if you are using any finite element software like Abacus or ANSYS or such. To properly obtain the hardening material parameters of this model, we had to conduct carefully executed monotonic and a cyclic coupon test for the calibration. Actually, I would like here you can see like here you can see like some comparisons with the coupon test and the calibrated material model. I would like to note here that this material model, along with the recommended values for the parameters for the different steel grades, has been already implemented in OpenSeas if you're using it. So please feel free to check this model and maybe use it in your fiber models and such. So in summary, all these modeling specifics and definitions make the modeling approach independent of the section size, independent of the loading history, independent of the axial load that's going to be applied and so on. So in that sense, it can be generalized to any scenario. Essentially, we did rigorous validation for this modeling approach with test data that I just showed, and also with test data from available in literature from other researchers. As you demonstrated here, we were able to capture the right instability modes and the moment rotational response and the progression, the complex progression of axial shortening due to local buckling. Talking about validation, it's Also worth noting that this approach was also further validated through the blind prediction contest organized by NIST and ATC last year, based on the full-scale column test conducted by Professor Shemeng Wang at UC San Diego. Now, as part of the ATC 114 project, we used this model to parametrically investigate the behavior of a typical 15 feet long first story column with flexible boundary conditions at the top. The parametric space included 60 wide-flange cross-sections, from shallow cross-sections to deep cross-sections, 3 different lateral loading protocols, 5 levels of constant compressive axial loads, which adds up to more than 1,000 simulations, more or less. Now, using the data from this simulation, we were able to develop seismic design recommendations. And essentially, we used the simulated responses to extract many response data related to the rotational ductility, the strength, and the stiffness deterioration. For instance, we evaluated the rotation at which you lose 20% of your plastic moment capacity. And based on all these parameters, we were able to propose improved design recommendations for a better ductility and stability in steel columns. So specifically, our target performance in this case was at 4% drift, that we need to limit the strength deterioration to 20% of MP, limit the stiffness deterioration to 50% of the initial elastic stiffness, and also to limit the amount of axial shortening to 1% of the length of the column length, which is roughly about 1 inch. So the recommendations included a refined upper limit for the column local slenderness, and essentially we proposed to push the current limit by a 2/3 to the left, as you see here. This is the limit for highly ductile members, or what's called, noted as lambda HT. At the same time, we proposed an upper limit for the gravity-induced axial load of 30% PY, and an upper limit for the global member slenderness of 80. Again, these are all to achieve this target performance that I showed earlier. But given that you have the data, you can provide or you can target any performance criteria that you would like and see which cross sections or limits on the loading you need to induce. Using the parametric data, again, we were able to conduct regression analysis and develop equations to predict key column response indicators. This includes, as you see here in this slide, the length of the plastic hinge region at the column base. And this equation, this regression equation that you see here, essentially captures the fact that stokier cross sections, the ones with a stokier web, in this case H/T web, will develop a larger plastic hinge length compared to a more slender column, due to the fact that local buckling is delayed and a large amount of cyclic hardening is developed that keeps propagating plastic strains to a higher elevations. Also, the same equation captures the effect of the axial load. Essentially, once you are getting higher axial load, the P delta moments, the second order P delta moments tend to push the plastic strains again to a higher elevation, and you start getting larger plastic hinge length. Now, such expression can be very useful when you are discretizing column regions, for instance, as part of a fiber-based modeling approach. It can also be useful in seismic design when you are trying to allocate or design the supplemental bracing, for instance. You can observe here from the R-square factors and the coefficient of variations for the errors that the model does overall a very good job capturing this variation in plastic hinge length with respect to those predictor parameters. Again, with performance indicator, we also developed another expression to predict column axial shortening. And the main controlling parameter in this equation, along with the web slenderness and the axial load, is the cumulative plastic rotation that the column experiences. And this parameter essentially makes this expression usable for any loading history. So again, this can be very useful when assessing structure performance at the system level or when evaluating column damage and the associated losses. Now, moving over to the development of nonlinear numerical models for steel columns that are commonly used in engineering practice. Basically, we need such models to conduct static and dynamic analysis as part of the performance-based engineering framework. And the ASC 41 standard historically provided such modeling guidelines. The 2013 issue was the standard actually at the time of the testing and the time of the study before being superseded recently by the ASC 41-17. Essentially, in both documents, the concept is to for steel moment frame components, ASC 41 provides you with this generalized force deformation curve shown here, where A and B are the main plastic rotation parameters. The curve is supposed to represent the skeleton or the envelope curve bounding the cyclic behavior based on symmetric cyclic loading. Essentially, we aimed to use the large data pool generated by the simulation data and from all the tests available in literature up to the point to develop updated definitions of the ferrous cycle envelope and to provide new definitions for the monotonic backbone curve shown here in black. Unlike the cyclic envelope that we have shown that it depends on the loading history, the monotonic backbone curve is considered a unique property of a structure member, and it can be used with available phenomenological component models that explicitly simulate the cyclic degradation mechanism in strength and stiffness. In that sense, you can use this for dynamic analysis, nonlinear analysis, regardless of the loading history or the seismic intensity your structure will be subjected to. In summary, the process involves conducting curve fitting to the test data, to the test and the simulation data, followed by multiple regression analysis, and finally, regression equations are developed and evaluated. I will not elaborate further on this due to the time, but you can always refer to the original publication shown here for the detailed statistical procedures. Here is, for instance, the equations for the proposed ferrous cycle envelope curve. And some of the key updates here is the fact that instead of providing constant rotation values based on discrete bins of cylinder ranges or loading ranges, these equations capture the variation and the change in all the parameters for all ranges of loading and geometric values. So it doesn't lump together different cross sections in the same pin. Otherwise, you are getting here the full variability in the parameters. The model also captures the variability in the post-yield slope with respect to the column parameters and the loading, the axial load. And this is compared to the constant slope that's used in ASC 41, which is 3% of the elastic stiffness. So here you can capture this variation in this slope. In the same time, rather than having a sudden drop in your moment rotation curve, once you reach your capping strength, which is the case in ASC 41, here the model captured the gradual post-peak slope or post-local buckling slope, which actually can also help with the numerical convergence issues when you are doing analysis. But most importantly, it captures better the overall behavior of your component. As part of these numerical models, we also had to reassess the axial load limit at which a column can be considered a force-controlled member, which means it has no plastic rotation capacity. Essentially, in the previous ASC 41 standard, the limit was about 40% of PY. So more than that, you will need to consider your column member to be elastic, and essentially it loses strength right after it yields. But this can be fairly conservative in light of the current data that we have. So by looking at the value of plastic deformation with respect to the axial load, we found that the new revised limit can be set or can be relaxed to 60% of PY, which is actually the limit used in the current ASC 41 standard, ASC 41-17. These are a couple of illustrative test data comparisons with respect to the first cycle envelope that we proposed. Also in the same plots, we superimposed the same envelope curve based on the previous and current ASC 41 standards. And these are for two specimens with different axial load levels under symmetric loading. As you can observe here, the ASC 41-13, this is the previous version, used to overestimate the elastic stiffness. And this is due to the fact that the contributions of the shear deformations were not included in the computation of the elastic stiffness. And this contribution actually can be substantial. It can easily reach about 20% in deep columns. And now this issue has been resolved in the current ASC 41 standard. Also, the previous standard, as I just mentioned, for a column subjected to 50% of its axial yield strength, you would consider this cyclic envelope curve, where essentially you have the elastic region, and then you drop right away in strength because you don't have plastic deformation, which is a force-controlled limit. Again, this has been revised as I just showed. With respect to the current ASC 41 standard, again, as I mentioned, the proposed model overall appears to fit the test data better. For instance, the post-yield hardening slope and the gradual decrease in the flexure strength in the post-buckling region reflects the actual behavior better. This is the same, again, these are all some evaluations showing good agreement between the proposed monotonic backbone curve and the test data at different axial load levels. I mentioned that these monotonic backbones can be used with phenomenological component models that simulate cyclic degradation, strength, and stiffness. And if you are a user of OpenSeas and such, you're probably familiar with the Ibarra-Medina-Karavinkler model, or the IMK model for short. And essentially what we did here is calibrations of these proposed monotonic backbones with this model in order to calibrate the rate of deterioration, which is captured by this parameter called lambda. So again, you can compute directly the values for lambda here and use it with these proposed monotonic backbones. And you can see for different loading histories, you just need the monotonic backbone definition, the value for lambda, and regardless of the loading history, you are capturing the behavior very good, I would say. Lastly, we also provided guidelines for or considerations for other loading scenarios. And in the case when you have what I talked so far is all based on constant axial load. So if you have a varying axial load, you can still use the modeling recommendations that I previously mentioned by looking only at the gravity load offset. But essentially you will get the same plastic deformation parameters, but what will happen is that when in excursions, when you have an increased axial load, you will be over predicting the strength. And in the other direction, in the opposite excursions, when the axial load decreases, you will be under predicting the strength. So an alternative would be to do an upper lower bound type of analysis maybe, or if you can use sophisticated material deterioration models that can capture these effects implicitly. For biaxial bending, again, with respect to the cyclic envelope, there is no significant difference when it comes to the plastic rotation parameters. The only thing that you will need to consider is the reduction in strength to account for the PM interaction, which you can actually do using the Codes equation. So I'm close to the time. So the last thing I'm showing is, again, this was the last part of the research, which is essentially the development of damage fragility functions. And the development of such functions was feasible given all this new test data. And this can, of course, can be used for loss assessment studies and such. So we developed univariate fragility curves as the ones you see here that take into account the loading history effect. So for local buckling, the difference between asymmetric loading and collapse loading won't matter a lot. But after that, once local buckling progresses, the probability of damage changes substantially based on the loading history the column is subjected to. Also, to reduce the uncertainty associated with univariate functions, we used ordinal logistic regression analysis to develop more accurate multivariate functions that considers the loading and the geometric parameters of the column to predict the probability of damage. Now, to summarize what I just presented, essentially, it's a coordinated testing and simulation and numerical research based on validated continuum finite element modeling approaches and full and large scale testing, that we use the data from this to develop seismic design provisions for improved ductility and stability in deep steel columns, to develop expressions for key column performance indicators, and to develop damage fragility functions to help with loss assessment studies. And we also provided guidelines for nonlinear modeling of steel beam columns with a new definition of the monotonic backbone curve that captures all these different phenomena that I discussed in the presentation. Please use the references here if you are interested in reading more on the column topics that I just discussed today, because I only mentioned brief observations. There are a lot more to it. I would also like to mention that if you're interested, the full processed experimental data will be publicly available online very soon. So keep an eye out for that if you are interested in those. And at last, thank you for your attention. And if you have any questions, please let me know.
Okay, if anyone has any questions, you can please unmute yourself or type it in the chat, and we will open up the questions now. Also, if there are any issues unmuting yourself, you could raise your hand through the chat window as well. Okay, there is a question in the chat, if you can see it, or if you want me to read out loud. Your revised design, you could go ahead and read it and answer.
Okay, 1 second. Okay, so the question says, your revised design recommendations suggested a limit on web slenderness, but it seemed like all columns buckled at the flanges. Is there a reason for no revised flange slenderness limits? Okay, that's a good question, actually. And well, if I go, let me show something here. If you look at the catalog of Wide-Flange steel columns, you will see that more or less there is a linear correlation between the web and the flange. So if you are putting a limit on one, you are also putting a limit, proportional limit on the other value. But the reason why we looked at the web slenderness is actually the fact that we did some nonlinear finite element analysis in the beginning, and we found that the web has higher correlation when it comes to column damage more than the flange. But in the same time, this revised design recommendations is not only related to the web slenderness per se, it's related to the compactness limit. So a 2/3 will be applied for the web and a 2/3 will be applied for the flange as well. So I hope this answers your question.
Okay, there's
yeah.
Oh, that's you yourself. Okay.
Yes, yes. So the second question is, for the effect of the boundary conditions, was the base boundary conditions considered? No. Actually, that's a good question. So for the time of the testing, there was essentially just for testing reasons, we had to assume a fixed base as you do in design. There are recent research that showed that actually there is some flexibility for the column-based connections and in the foundation. This was not considered in these tests, but again, this is something to be looked at. And actually, there is several research publications discussing the effect of this flexibility on the overall column behavior. But as you have seen, this is not considered here in this test, only the top flexibility. Okay, so The other question, thank you for the presentation. Could you please explain briefly the bidirectional control algorithm for your test specimen? That is the actuator displacement, command, feedback, vertices, specimen displacement, feedback, or recommend an article that explains the details of the testing. Well, this is a quasi-static testing. So essentially we were applying, if I show the slide again, we were applying the drifts in displacement control at the top of the specimen. So, and then we're reading back the force reaction. And the same thing with respect to the rotation, we're applying the rotation. The only thing that we are applying in force control is the axial load. So there was no issues related to the displacement command or feedback, which I think is your question. But you may refer to this publication over here for more details about this control system and how we use it for such types of testing.
Okay, we'll hold for 1 or 2 more minutes for any more questions. If anyone's typing, get them some time.
Sure.
And Chad, I'm not sure if you're still listening in, if you have any closing remarks as well, just if there are any. Okay, I think we'll conclude and let everybody go out, get some lunch, get some fresh air. We appreciate you taking the time for presenting this material. Very informative, a lot of good science going on here, and what you're presenting, I think the community is really going to benefit from. So again, thank you. And as far as the NERI LEHIGH seminar series, for the audience, we will have more in the future coming in 2020 that we're going to be presenting soon. So keep an eye on your announce emails from the Design Safe team. And if there are ever any questions or comments that you want to send to us, please, you could find our contact information through the LEHIGH EF page on Design Safe, or contacting us directly, myself, Thomas Murillo, or Chad Cusco at LEHIGH. So again, thank you, everybody. And again, to the presenter, Dr. Kadi, thank you so much.
Thank you, Chad, for having me, and for everyone, thank you for listening. And if you have any further questions at any time, just please feel free to email me, and I will be very glad to respond and discuss things further. Thank you.
And are you okay with us archiving the video of this presentation to put on the web for everybody?
Yeah, sure,
okay.
Sure, definitely.
Thank you.
Definitely. All right.
All right.
Thank
okay,
you.
I'll end our meeting for today. Thank you.
Thank you very much. Thank you.